Hey guys, I'm Bout with Math and I'm going to be showing you what is a derivative. So in order to visualize the derivative, I'm going to draw a graph of the function f of x equals x squared plus 2, which would look something like this. This is 2. Now, let's say we had 2 points on the graph, right here and right here, where this first point we'll label as x, f of x, as you normally would. Y or f of x, in this case I'll use f of x. And then this point here we'll label as x plus h, because that's been moved h amount from the original x, and then f of x plus h to account for the difference as well. In order to find out the slope of this line, we would use the formula m equals y2 minus y1 over x2 minus x1. But now, I'm going to rewrite this formula using these points. So our m would be y2, or y2 would be f of x plus h, minus y1 f of x, over x plus h, it's our x2, x plus h, minus just x. So if we were to simplify this, these x's would end up canceling out, x minus x, and we'll end up with f of x plus h minus f of x over h. So this would represent the rate of change between x and x plus h of the function. And this line here represents our secant line where 2 points are being intersected. But let's say the line were to narrow down to only 1 point, and it would look something like this. Now here, this is called a tangent line, where the line intersects the curve at only 1 point. How do we find the rate of change of this if there's no h anymore? Well, we can see that the points, we can imagine them coming closer together and approaching this line. And knowing what we know about limits, limits are about approaching a certain value. So we can rewrite this slope formula as the limit as h approaches 0, because h has gone away here, of f of x plus h minus f of x over h. And this limit will show us the rate of change that occurs at this specific point on the function. Now, how would we go about solving that for this function? Let's take f of x equals x squared plus 2. And let's apply that to the limit. So, the limit as h approaches 0 of f of x plus h is x plus h squared plus 2. Here, I just plugged in x plus h for every x that we had, which is just x squared, minus f of x, which would just be x squared plus 2, all over h. Now, obviously, if we plug in 0 to h, we don't end up getting an answer. So we're going to have to work with our expression. So x plus h squared is x squared plus 2xh plus h squared plus 2, and then distribute the negative, minus x squared minus 2, all over h. Now here, we'll notice that the negative x squared and the x squared cancel, and the negative 2 and positive 2 cancel. So we can rewrite the limit as 2xh plus h squared over h. And we can factor out an h from the numerator. 2x, right? H, 2x, and then plus just 1h, because we factor out the h, all over h. And then we can cancel out our h's, so we're left with the limit as h approaches 0 of 2x plus h. And once we plug in 0, when this is 0, we end up with nothing, so we're just left with 2x. So this is known as the limit of the difference quotient, and after applying that limit to f of x equals x squared plus 2, we end up with 2x. This is also the derivative of our function, meaning that this represents the rate of change of our original function. And in math, we'll denote that as f prime of x equals 2x in comparison to our f of x. However, this doesn't answer a question of the rate of change happening at this tangent line. This does not look like 2x. How to find this is, we use our derivative now to find this rate of change. So let's say this point here was x equals -2 at this specific point. What we'd do is we'd find f prime of -2, and then we just plug it in. 2 times -2 equals -4. And as you can see, this is a steep line going downward, which is similar to our -4 right here. So in essence, the limit of the difference quotient is how we find our derivative. Now, it could be very tedious to do that limit all over for so many functions, and some of them kind of hard to do. So derivatives have rules acquired. So the main rule used in differentiation is known as the power rule, which means that if you're taking the derivative, this d over d is an operator, and then our variable x, which means in respect to x. If you're taking the derivative in respect to x of x to the nth power, where n is some sort of number, and x is your variable, you can drop the exponent, right, and multiply it by your variable, and then for the power of your variable, u minus 1. So how would this look? Let's use the same exact example we had, d over dx of x squared plus 2. So with the power rule, you do it term by term. So let's focus on the first term. X squared, we're going to drop the 2, right? Multiply it. Then we have times x, 2x, and then 2 minus 1. And then for our second one, plus 2. Now this 2x, you can visualize as 2, sorry, not 2x, just 2. This 2 you can visualize as 2x to the 0th power. So we can say plus, we're going to have 2 times, now we're going to drop the n. We're going to drop the n. So we're going to end up getting 0 times 2, and then x, 0 minus 1. Now, we're multiplying by 0 here, so anything multiplied here will just end up as 0. And then we're going to have here 2 times x to the 2 minus 1, 2 times x to the 1, so that's just 2x, plus 0, meaning that our derivative would be 2x of this function, which checks out with what we had earlier. The power rule only works for functions written in polynomial form, meaning that functions like radical functions, exponential, trigonometric, and logarithmic functions cannot be differentiated so easily. But that's not always the case. If we have the derivative of 1 over x, we can rewrite this as the derivative of x to the negative 1. And now it is in polynomial form. And then we'll just apply the same thing. We're going to times it by negative 1, keep the x, and then negative 1 minus 1. So end up getting negative times x to the negative 2. And we can rewrite this in rational form as negative 1 over x squared. The same thing applies for radical functions. Say we had the derivative of the square root of x. We can rewrite this as the derivative of x to the 1/2, which means that we'll drop 1/2 times x to the 1/2 minus 1, which this would be 1/2 minus 2 over 2, which is just negative 1 over 2. So now our final derivative would be, our final answer would be 1/2 times x to the negative 1/2. And to rewrite this in radical form, we would have 1 over 2 times the square root of x. The 2 on the bottom, and then the x, the negative exponent brings it to the bottom, and the 1/2 makes it the square root of 2. So these are examples in which you can take the derivative of rational and radical functions. However, note that the power rule will only work for polynomial style functions, including even those radical and rational, where only one term was in the denominator or only one term was in the radicand. So if we had something like f of x equals x squared plus 2, the power rule no longer works because you cannot convert this to, you just can't convert this to polynomial form. When you try, you end up getting x squared plus 2 to the 1/2, and you can't take the derivative of this anymore. It doesn't work. You'll need to use the chain rule, which you learn later on. The same thing occurs if we have g of x equals 3 over x squared plus 3x. This, you cannot take the derivative of this either. You cannot convert this into, like, it's very weird. So these require you to use either the quotient rule or the chain rule, which I will cover in a later topic. I hope you guys understood what a derivative is now, and that you'll be able to find the rate of change of any polynomial function.